Okay, so welcome back. Today we're going to do some more statistical inequalities. We're going to do Chebyshev. We are going to do, that's the last one we're going to do actually. Then we're going to move on. We're going to do the Cauchy-Schwarz inequality. We're going to look at correlations. We're going to talk a bit about expectations, particularly conditional expectations and something called the law of iterated expectations, which are both very, very important in econometrics. Then we're going to move on and we're going to study something called a moment-generating function. I'm going to show you that a moment-generating function characterizes a distribution. I'm going to show you how one can derive any moment of a random variable from its moment-generating function. Okay, so a moment-generating function will be the last thing we get to, most likely. So let's go back to our inequality. So last time we proved the Markov inequality. The proof was quite straightforward. We proved that for a non-negative random variable x, the probability that x is larger than some constant a, some positive constant a, is less than or equal to the expectation of x divided by a. So that's very useful. One which is a little bit more useful is Chebyshev's inequality. So what Chebyshev's inequality does is it allows us to put an upper bound on deviations of a random variable from its mean. Okay, so we can ask questions. We know for any random variable how close it will be to its mean in probability. We can make a probabilistic statement on that. Okay, so Chebyshev's inequality says that the probability that the absolute value of x minus its expectation is larger than some constant a is less than or equal to the variance of x divided by a squared. Okay, so that is very, very useful inequality indeed. So I'm going to prove it, and then I'm going to talk a little bit about a second form you might see, and then how one might go about using it. So let's start by proving Chebyshev's inequality. So on to the doc-cam. So to prove Chebyshev's inequality, all we're going to do is use the Markov inequality. Okay, so this is the Chebyshev inequality. Okay, so what we're going to do, we're going to define a random variable y, and y is equal to x minus e of x squared. So that's a random variable y, it's a function of x. Now, clearly, y is a non-negative random variable. It is something squared, cannot be negative. Okay? So, since y is greater than 0 always, we can apply the Markov inequality. So let's do that. Well, the Markov inequality is p probability that y is greater than or equal to a squared is less than or equal to e of y over a squared. Now I'm using a squared here rather than a, as I used in the Markov inequality, but it doesn't matter. It's still a positive number, a squared. Okay, next step is to substitute in what is y. Well, we defined y up here, so we're just going to plug it in down there. So then we have that the probability that x minus its expectation squared is larger than a squared is less than or equal to, what is this? Expectation of y, so that is x minus e of x squared divided by a squared. Okay. So now we're going to do something to the left-hand side and something to the right-hand side. On the right-hand side, you'll notice that this here is just the variance of x. It's the expected squared deviation of x from its mean. Okay, so all I'm going to do is plug in variance there. It's the same thing. On the left-hand side, we've got something squared. We've got an event which is something squared greater than or equal to something else squared. I'm just going to take the square root of both sides, and that's going to preserve the inequality. Okay. So what we have on the left is the probability of the absolute value of x minus e of x greater than or equal to a. So that's just taking the square root of both sides, making sure we don't lose the fact that this could be negative. And here I'm just going to plug in the variance, because that's what it is less than or equal to the variance of x divided by a squared. And that's it. That's the Chebyshev inequality. Okay, so all we do is we apply the Markov inequality, and we apply it to a random variable, which is another random variable minus its expectation squared. We do a little bit of rearranging, we use the definition of variance, and we end up with Chebyshev inequality. Okay, all good? Yep. So that's just plugging formulas into the Markov inequality. Okay, let me go back to the desktop. So the Chebyshev inequality can be expressed in two forms. One is the form which I just showed, where we have an A. What you might see typically in an introductory text would be to take A equal to some constant k multiplied by the standard deviation of x. So if you use A equals k times sigma, where sigma is the standard deviation of x, you can plug those things in to the formula above, to this one here. You might see the Chebyshev inequality expressed like this sometimes. Now, why is this useful? Because now we can ask questions about deviations of a random variable from its mean in terms of its standard deviation. So, for example, if we set k equal to 2, what we have is that we can say that 75% of observations are going to fall within 2 standard deviations of the mean. Okay, that's if you took k to be 2. The 1 over k squared is going to be a quarter, and the k sigma is going to be 2 sigma. So you can say that 75% of observations will fall within 2 standard deviations of the mean. If you take different k's, you can change that statement, and that's very, very useful in practice. So there's going to be a couple of questions like that in the tutorial. Okay.
Sorry.
Yes?
Where does the 75%
Because 1 over k squared is 1 over 4,
All right.
which is 0.25,
Okay.
and it's 1 minus 0.25. Yeah? Okay. Okay. All right, let us progress. So what I'd like to define now is how to take suppose we have a bivariate random variable, and we want to compute the mean of some function of that bivariate random variable. So I have 2 random variables, x and y. I have a function, g of x of y. X and y have a joint distribution. How then do I compute the expected value of g of x and y? Well, it's very simple. You just integrate the function gx of y multiplied by the joint PDF, fx of x and y, over x and y. Okay, that's how you take the expectation of a function, of a bivariate function of a random variable. So you would just plug in this formula here. Obviously, we require that the density function should exist. Otherwise, if the PDF does not exist, you have to use the formula for the CDF, which is this one. So why define that? Well, because that allows us to define something called covariance. Okay, if I choose a particular g of x and y, then I can define something called covariance. So the covariance, which you might sometimes see as denoted by sigma, the covariance of x and y is the expectation of the product of x minus e of x and y minus e of y. So our g from just a second ago is going to be this function in here, x minus e of x, y minus e of y. Now, it's very straightforward, and I'll leave it as an exercise. It's very straightforward to show that you can rewrite that as the expectation of x times y minus the expectation of x times the expectation of y. Have a try at that. It's pretty straightforward, which you should all be familiar with, because if y were equal to x, then that would be the standard formula for variance, which you've probably all seen, well, which you have all seen before. So that's what we call the covariance. The covariance is a measure of linear dependence between x and y. Okay. So it's not a measure of independence, it's a measure of linear dependence. I'll talk a little bit more about the relation with independence later. We can work something out about the covariance, which is something called the Cauchy-Schwarz inequality. So for two random variables, x and y, we have the following inequality. It's that the squared covariance is less than or equal to the product of the variances. Okay, that's something called the Cauchy-Schwarz inequality. It allows us then to define something called a correlation coefficient. But let's first prove the Cauchy-Schwarz inequality, that the covariance squared is less than or equal to the product of the variances. Okay, so to my .cam. So we're going to prove Cauchy-Schwarz. So this is what we're going to prove. Cauchy-Schwarz. Okay. Now what we're going to do, we're going to define a random variable. Let's call it z, just for now. And z is going to be the following. It's going to be x minus e of x minus lambda y minus e of y. That's going to be our z. And lambda, for now, is just a constant. I'm going to use a particular value of lambda in a minute, but lambda is just a constant. Okay? So, clearly, the expectation of z squared is greater than 0. No matter what lambda, if I take the expectation of something squared, it's greater than 0. Okay? Any lambda, this applies for any value of lambda that I choose, the expectation of z squared is greater than 0. Yep, because why? Because z squared is greater than 0, always. Okay, so that applies for all lambda in R. Okay, well, we can work out what is z squared. It involves a little bit of algebra, but it's not too complicated. So, if you plug in z there, take the expectation of it, then you have that the variance of x plus lambda squared times the variance of y minus 2 lambda cov x y is greater than or equal to 0. Okay, so if you compute the expectation of z squared, plug in what is z, you should be able to show that the expectation of z squared is all of this on the left-hand side. Okay, I'll leave that as an exercise. It's relatively straightforward to do. So again, this is for any lambda. Now what we're going to do is we're going to take a particular value of lambda. And this particular value of lambda is what is going to give us the Cauchy-Schwarz inequality. So I'm now going to set lambda to be the covariance of x and y divided by the variance of y. That's the lambda we're going to use. Okay. So now we plug that lambda in here. So what have we got? We've got variance of x plus cov x y squared times vy divided by Vy squared minus 2 cov xy squared over Vy is greater than or equal to 0. So that's what I get if I plug in this lambda into there. Okay. So, you'll notice now that a few things are going to cancel. This variance of y, we've got a variance of y squared on the bottom, so that's going to go. And we're going to end up with the following. What are we going to have? We're going to have variance of x plus covariance of x and y squared over the variance of y minus 2 times the covariance of x and y squared over the variance of y is greater than or equal to 0. Now here we have a plus 1 of this term, here we have a minus 2 of exactly the same term. So overall we end up with the variance of x minus the covariance of x and y squared divided by the variance of y is greater than or equal to 0. And now we just rearrange that to get it in the form I wrote on the slides, which was that the covariance of x and y squared is less than or equal to the variance of x times the variance of y. Okay, so in sum, what did we do? We considered z, which was this random variable here, x minus its expectation, minus lambda times y minus its expectation. We know that z squared is a non-negative random variable, therefore its expectation is also non-negative. That's here, and that's true for any lambda. We can compute this expectation, the expectation of z squared. It's going to be the variance of x plus lambda squared, the variance of y, minus 2 lambda times the covariance of x and y. I didn't do that for you, I'm going to leave it as an exercise. Then we choose a particular value of lambda. The value we use is this one, the covariance of x, y divided by the variance of y. Plug that in, do some algebra, and eventually you get the result. Okay, so nothing more than relatively basic algebra there, and using a cleverly chosen value of lambda. Okay, let's go back to the desktop. So we've got now a Cauchy-Schwarz inequality, which is that the covariance of x and y squared is less than or equal to the product of the variances. We can now define something called a correlation coefficient. Correlation coefficient typically is denoted by rho. So you have a correlation coefficient of 2 random variables, and this is the covariance of x and y divided by the square root of the variance of x times the square root of the variance of y. That's called the correlation coefficient. Now, you can see immediately from the Cauchy-Schwarz inequality, let me go back to that the numerator is going to be less than or equal to the denominator, okay, in absolute value. Why? Because we have that the covariance squared is less than or equal to the product of the variances. That's Cauchy-Schwarz. Here we can just take the square root of both sides. If you divide then the covariance by the square root of the product of the by the product of the square roots of the variances, you're going to get, using the Cauchy-Schwarz inequality, that correlation coefficient, rho of x and y, is always less than 1. That follows immediately from the Cauchy-Schwarz inequality. So how do we interpret rho x and y? How do we interpret the correlation coefficient? Well, the correlation coefficient, again, it's just a rescaling of the covariance. The covariance measured linear dependence. if I rescale the covariance, it's still a measure of linear dependence. Okay. What does it mean? Well, we know that it's less than 1 in absolute value. So what if it's close to 1? If it's close to 1, or more precisely, if it is exactly 1, then we say that x and y are linearly dependent, and there's a positive linear dependence. That means that I can write, if the correlation coefficient is 1, I can write x as a linear function of y. And the slope is going to be positive. Okay, so I can write x is equal to a plus by, where b is a positive number. That's what I could say if the correlation coefficient were exactly 1. If it's minus 1, then we would have a perfect negative correlation. So again, I could write x and y as a linear function of one another, this time with a negative slope. Okay. So we say that a pair of random variables, they are linearly independent if and only if the covariance is 0. Clearly, if the covariance is 0, the correlation is also 0. Which is equivalent to the statement that the expectation of x times y is equal to the expectation of x times the expectation of y. So that is the definition of linear independence. We can say that they're linearly independent if they have 0 covariance or if they have 0 correlation. Same thing. Now, independence implies linear independence. So if x and y are independent, you can show that they are linearly independent. But the converse is not true. X and y can have 0 covariance, but they can be dependent. Okay? 0 covariance is not enough for independence, just to be clear. It is enough for linear independence. Okay, let us move on. Let's talk now about conditional mean and variances. So, I showed you how to define an expectation. Now what we're going to do is work with conditional expectations. So, what is the conditional expectation? It is the expected value of a random variable with respect to the conditional probability distribution of the random variable. Okay? So if f of y given x is the conditional density of y given x, then the conditional mean is just the expected value of y at that particular value of x. So we fix x, and at that value of x, we ask what is the expected value of y. To do that, we need to use the conditional distribution of y given x at the point small x, where we fix x. And then we just use the usual formula. It is the integral of y multiplied by f of y given x with respect to dy. Now this conditional expectation will typically be different at different values of x. Okay? If x is 1, the expected value of y given x is 1 could be 2. If x is 0, the expected value of y given x could be 0. Okay? So it will depend on the value of x at which we fix, at which we take the expectation of y in general. Clearly, if x and y are independent, it won't. But in general, it will. We'll get a different value for different values of small x. Okay, then in a similar way, so that was conditional expectation. In a similar way, we can define a conditional variance. So, what is that? It is asking what is the variance of y when I fix x at a particular point. Okay, I fix x somewhere. X can be 2, for example. Then I look at the distribution of y given x. I compute the variance of y given x at that point. So how do we do that? Well, we just use this formula here. So it is just the expectation using the distribution of y given x of y minus e of y all squared. Alternatively, you can write that as the expectation over the distribution of y given x of y squared minus the expectation over the distribution of y given x of y all squared. okay, which should be familiar. It's similar to the standard variance formula. The only difference is our expectations are with respect to the conditional distribution rather than the marginal distribution. Okay, so that's how one defines conditional mean and variance. Now we have two very important laws. One is called the law of iterated expectations, which is the first one on the screen, just this one here. One is called the law of iterated variance. The law of iterated expectation is very, very important, particularly for regression analysis, because it is crucial to prove things like unbiasedness or consistency. Many of the results that you'll see for in regression analysis depend on the law of iterated expectations. Okay. The law of iterated variance is also quite useful, possibly not quite as useful as the law of iterated expectations. So what I'm going to do now is I'm going to prove both of them, so you can see where they come from. So let me do that. So we're going to start with iterated expectations. To my docamp. Okay, iterated expectations. So I'm going to do a proof for the case where we have continuously distributed random variables. The case for discrete random variables is very similar. You're just going to replace integrals with sums. Okay, so I'm just going to do the proof in the continuous case. So, okay, this is iterated expectations. All right. So we're going to start with the following. I'm going to write e of x, e of y given x, so we're going to take the expectation of, with respect to the distribution of x, of the conditional expectation of y given x. So at each small x, we have a corresponding value of e of y given x. Now I'm going to average over all of those small x's. And we're going to show that we end up with eventually the expectation of y. Okay, so at each small x, we have an expectation of y given x. We're going to average over all of the small x's, and we're going to get expectation of y. Okay, so let's write down what is this. Let's deal with the outer expectation first. The outer expectation, because I'm doing the proof for continuous random variables, the outer expectation is an integral. And I'm going to leave what's in the inner expectation the same. That's e of y given x. Then I'm going to have an fx of x and a dx. Okay. So that's the expectation of this over the distribution of x. All I'm doing is I'm averaging this function here over the distribution of x. Okay. Next step is to plug in what this expectation here is. So that is, I'm going to keep the outer integral the same. Now I'm going to plug in for the conditional expectation of y given x. So again, that is an expectation, so we have an integral. Go between minus infinity and infinity. We're taking the expectation of y with respect to the conditional distribution of y given x. So here I'm going to have a y. Then I'm going to have a conditional distribution of y at point small x and a dy. Okay, so that's what this expectation here is. I'm not going to change anything with respect to the outer expectation, so I'm going to keep my fx of x and I'm going to keep my dx. Okay, so now we have a double integral. We're integrating something over y and x. The next thing I want to do is I'm going to replace this conditional distribution here. I'm going to use the definition of conditional distribution and plug in what that actually is. Okay, so my outer integral is going to stay the same. It's minus infinity plus infinity. I'm going to keep the bracket. Here I'm going to keep the minus infinity plus infinity. I'm going to keep the y. I'm going to substitute in this now, which is going to be the joint divided by the marginal with respect to x. I'm going to keep the dy. I'm going to keep the fx of x and the dx there. So that is just the definition of the conditional distribution. Okay, now clearly this guy and that guy are going to cancel out. We're multiplying something by fx of x, we're dividing something by fx of x. So those two are going to go. Okay, so what we're going to have is a double integral like that. Then we're going to have a y, going to have an fx y of x and y. I'm going to have a dy and a dx. Okay, so that's just cancelling out the fx of x. Right. Next thing, what we're going to do is reverse the order of integration. Now, I don't want to get into why we can reverse the order of integration here. If you're interested, you can look up conditions under which the order of integration can be reversed. Here, we're integrating between minus infinity and infinity, or we're integrating something continuous, so it's very straightforward. Okay, it involves, I'm not going to prove that I can reverse the order of integration, but just take my word that in this case I can. Okay, so that is minus infinity, infinity, minus infinity, infinity, y, fxy of x and y, dx, dy. Again, as I said, in this case I can reverse the order of integration. It's not always the case, but this time we can. We're integrating between minus infinity and infinity for everything, and we're integrating something which is well behaved, continuous, and so on. Okay, so now what I'm going to do is I'm going to take this y out of this inner integral, because in this inner integral y is constant. The inner integral I'm integrating with respect to x, so I can treat y as constant, which means I can take it out. So I can write a y there, minus infinity and infinity of fxy, x and y, dx, dy. And I'm just going to put a bracket there. Okay, so I've taken the y out. I can do that because it's constant in the inner integral. Now, hopefully, we recognize what's in the bracket here. I'm integrating the joint distribution of x and y with respect to x. So what I end up with is the marginal distribution of y. Okay, so this, in this bracket here, this is nothing but the marginal distribution of y. So what I have, minus infinity to infinity, y, fy of y, dy. That, by definition, is the expectation of y. So we're done. Alright, so what do? We started with what we wanted to evaluate, the expectation with respect to x of the conditional distribution of the conditional expectation of y given x. We just plugged in everything. Then we used the fact that we used the definition of the conditional distribution there. So this guy and that guy cancel out. Then, that's this line here. Then I reverse the order of integration. I didn't tell you why, but you can do that in this case. Then y is constant in this inner integral, so I can take it out there. What we're left with in brackets is the integral of the joint with respect to x. The integral of the joint with respect to x is just the marginal of y, and then we end up with the integral of y times its marginal, which is the expectation. And that's what we wanted to show. Okay, so now let me go back to the desktop, just briefly. So we've just proved the law of iterated expectation, which is this one here. The expectation of y is equal to the expectation with respect to x of its conditional expectation. What we're going to do now is prove the second thing, which is the law of iterated variance. Okay, and this actually is much simpler. We're just going to make use of the law of iterated expectation in the proof. So it's not going to be any integration here. You can prove it with integration if you want to, but you don't need to. Okay, so let's do that. So back to my .camp. Okay, so to do this, we're going to consider the expectation of two different things, and then we're going to sum them both up. And everything's going to cancel very nicely, and we're going to end up with what we want. So this is iterated variance. Okay, so the first, I said I'm going to take the expectation of two things and I'm going to add them together. The first thing I want to do is I want to take the expectation with respect to x of the variance of y given x which is this guy. So I'm going to take the expectation over x of the variance of y given x. Okay, the variance of y depends on x. I'm going to average it over all x's. That's what we're doing. So now just plug in the formula for what is the variance of y given x. It was on the slides a minute ago. I'm going to move down there because the expression is rather long. It is the expectation. So I'm going to keep the outer expectation. And in here we've got expectation over the distribution of y given x times y squared. Of y squared. Here is going to be the expectation of the distribution of y given x of y given x all squared. It's that. That's just plugging in what is the variance of y given x. It's the expectation of y squared given x minus the expectation of y given x all squared. Right, let's do this term by term then. So the first term is equal to expectation with respect to x of e of y given of e of y given x y squared given x. That's our first term. Second term is expectation with respect to x of this guy all squared. Okay. So this first term now, what we're going to do to the first term is just apply the law of iterated expectations. We have the expectation with respect to x, or the expectation of y given x. This time there's a y squared, but that actually doesn't matter. We can still use the law of iterated expectations just for y squared here. What we get, applying the law of iterated expectations, is that this is just the expectation with respect to the distribution of y squared. That's the first term. So that's applying the law of iterated expectations. Okay. The second term I don't want to do anything with it. I'm going to call it, I don't know, A. We'll deal with that later. That's going to cancel out in a minute. So the second term, I'm just going to call it A. Okay, so we've computed what the expectation over the distribution of x of the conditional variance of y is. It's this. Now what we're going to do is we're going to compute the variance with respect to x of the expectation of y given x. Bear with me. So now what I want to compute is the following. Conditional variance, the variance over the distribution of x of e of y given x, y, like that. Okay, so that's what I'm going to compute now. So again, this guy here is a random variable, depends on x. I'm going to compute its variance. Okay, well, we can just use the variance formula. So that is that this is the expectation over x of e of y given x all squared. So squared inside the bracket there, squared inside the expectation, minus the expectation with respect to x of e of y given x y given x equals x, and I'm going to square outside this time. Okay, so that's what that is. Right. The first term, this term here, should be familiar. It's what I called A earlier. Okay, so I'm just going to write A again. The second term is this here. So it's the expectation of x, of the expectation of y given x, and then we're going to square the whole thing. Here I can use the law of iterated expectations. So what is this? It is the expectation of y squared. Yep, that's using the law of iterated expectations there, and we've got to square it. Okay, so now I want to get rid of these two a's. What I'm going to do is I'm going to add the two things I just computed together. We're going to have a plus a and a minus a, and the a is going to go. Right? So, let us do that. So, we're going to have that e of x, v of y given x. That was the first thing I computed, plus the second thing I computed, which is this. So it was, we had, that was, the first term was this. We had the expectation of y squared minus a. The second term was a minus the expectation, minus the expectation of y all squared. Clearly the a's cancel. Then we have the expectation of y squared minus the expectation of y all squared, which is the variance of y. And that's it. That's the end. Okay, and that's called the law of iterated variance. So to prove the law of iterated variance, all you need to do is use the law of iterated expectations, construct a sum of two things. I showed you which sum you would want to use, and then use that, the nasty term, which was what I called A, cancels with itself when you add them together. Okay. Okay. So that's the law of iterated variance. Let's go back to the desktop. How are we doing? This might be... Yeah, this is a good time to take a break. So we'll start again. It's 12:45. We'll start again at 12:50. Okay. I've got a few things to get through. So just 5 minutes today. Okay, let us resume. Someone just asked me about the formula for the variance of y expressed in terms of the expectation of y squared and the expectation of y all squared. So in case it wasn't in the notes last week, a very, very useful thing to know is the following. It is that the variance of y is equal to the expectation of y squared minus the expectation of y all squared. That's an equivalent way of expressing the variance. Okay, the variance, you could also write it as the expectation of y minus e of y all squared. So that's the definition you've seen. From that definition, it's very straightforward to get the following, the first line. Okay? Just to make sure that that's somewhere that you can access. Okay. Let me now go back to my desktop. So, okay, we have done conditional mean, we've done conditional variance, we've now proven the law of iterated expectation and variance. So, last week we covered, so change of topic now, just briefly. Last week we covered linear transformations of bivariate random variables. That is, you have two random variables, x1 and x2. You have two other random variables which are a linear function of x1 and x2. Let them be y1 and y2. I showed you how to derive the distribution, the joint distribution of y1 and y2. Now, what I showed you applied to the linear case. That is, y1 and y2 should be linear functions of x1 and x2. So what I would just like to show you briefly is how to generalize that to the case where we don't need linearity. Okay, so I'm going to do now a generalization. I'll give you the equivalent formula for the case where we don't assume linearity. Okay, so now consider a general transformation. We have, again, two random variables, x and y, and now we have two other random variables, u and v, which are functions of x and y. So what do you do in the general case? First, it's the same step as the linear case. You would solve to get x in terms of u and v, and y in terms of u and v. Then you compute something called the Jacobian. The Jacobian is, it's a matrix. We haven't really done any linear algebra on this course, so you don't need to know what a matrix is at this stage. All you do is you write a 2x2 block of partial derivatives. Okay? That is, you need to differentiate x with respect to u, y with respect to u, x with respect to v, y with respect to v. And then what you need to do is compute something called the determinant of the Jacobian, which is just this formula here. So it's just the product of the partial of x with respect to u and y with respect to v minus the product of x with respect to v and y with respect to u. That's something called the Jacobian determinant. Now, you don't need to worry about a matrix algebra or anything. Just know that this is something called a Jacobian determinant. That's how you calculate it in the bivariate case. Okay. The formula then that you would use in the end, and I'm going to do an example in just a moment so that we can all see the steps involved. The formula then would be that the joint distribution of u and v is equal to the Jacobian determinant multiplied by the joint distribution of x and y evaluated at x of u and v. So x is the value of x when u is small u and v is small v, and the same for y. Right. So I'm just going to do an example because I think the example will make things much clearer. But the steps are the same for the linear case. What changes is what changes compared to the linear case is this bit here. The Jacobian determinant is something else. All right. So let me do an example. So the example we're going to do is as follows. Suppose that we have y, which is equal to x1 plus the square root of x2. And we have z, which is the square root of x2. So clearly, y and z are non-linear functions of x1 and x2. And we have a density for x1 and x2. It's a simple one. Just going to do the case where x1 and x2 are uniform on the 0, 1 square. And what we would like to do then is find the joint distribution of of y and z given this information. Okay. So we're going to go through the steps I just outlined on the previous slide. I'm going to do it on the DocCam. So let us do that. Skip to my DocCam. So we had, so this is an example. So what we have is as follows. We have y was equal to x1 plus the square root of x2. Then we had z was just equal to the square root of x2. And we had that f x1, x2 of x1 and x2 is 1 if they're both between 0 and 1. And it was 0 otherwise. Okay, so that's the example. So step 1, what we're going to do, first thing we're going to do is we're going to solve so that I can express x1 and x2 in terms of y and z. Okay, so step 1 is that. So let us do that. What we're going to get, well, x1 is y minus the square root of x2, and z is the square root of x2. So x1 is y minus z. Okay, so that's x1. Obviously, in this example, it's very easy to solve for x1 and x2. In general, it might be more difficult in the non-linear case. But I won't ask you to do it if that step is hard. The second one, we had that the square root of x2 was equal to z. So then x2 equals z squared. Okay, so now we've written x1 and x2 as functions of y and z. Next thing we need to do is compute the Jacobian determinant. So I'm going to write down the Jacobian, j of y and z. So what is that? Now we've got to take each of these things and we've got to differentiate them both with respect to y and z. So we're going to have four derivatives. Okay. So the Jacobian determinant then is going to be, sorry, the Jacobian is going to be d of x1, but I'm going to sub in for x1 y minus z by dy. That's going to be top left element. Then we're going to have dy minus z dz. Then we're going to have so now we're going to do x2. So x2 is z squared, so it's dz squared by dy. And here we're going to have dz squared by dz. Okay, so the first row I'm doing x1 and I'm differentiating it with respect to y and z. In the second row I'm doing x2 and I'm differentiating it with respect to y and z. Okay, so the rows, there are two rows, they correspond to x1 and x2. There are two columns, they correspond to differentiating with respect to y and differentiating with respect to z. Okay, so we've got four things. We can work out what all those things are. So the top left element, I want to differentiate y minus z with respect to y, that is 1. This element here, differentiate y minus z with respect to z, it is a minus 1. This element here, dz squared by dy, that is a 0. This element here, dz squared by dz, that is a 2z. So that's what those things all are. Okay. Now what I need to do is I need to take the determinant, so I'm just going to use the formula which is in the slides. The way of remembering this in the 2 by 2 case is you just take the product of these two guys, top left and bottom right, and multiply it by the product of these two guys. Sorry, and subtract. Let me say that again. Let me say that again. Sorry, ignore what I just said. You take the product of this guy and that guy, and from that you subtract the product of this guy and this guy. That's the same as the formula in the notes. So that is 2z times 1 minus 1 times 0. Clearly there's a 0 there, so that goes, we end up with 2z. Okay, so that is your Jacobian determinant. So I'm going to write it as j of y and z with an absolute value sign around it. Okay, so nearly there. Now we just need to plug that into the formula. So what we have, plugging everything in to the formula on the slides, what we get is that f of y and z is equal to the Jacobian determinant, so that's 2z times f of x1, x2 of the values that we solve for, which are y minus z and z squared. Okay, so that's just plugging in the formula. Here we have a 2z. There we have the joint distribution of x1 and x2. We evaluated at the values of x1 and x2 expressed in terms of y and z. This guy was just 1, provided that x1 and x2 were in the appropriate box. So overall we get it's 2z times 1 if 0 less than or equal to y minus z less than or equal to 1, 0 less than or equal to z squared less than or equal to 1, and it's 0 otherwise. Okay. So, to summarize, what we do. Step 1, solve for x1 and x2 in terms of y and z. Step 2, compute the partial derivatives of x1 and x2 with respect to y and z. So you need to do that. You need to do 4 operations. You get this. Step 3, compute the Jacobian determinant using the formula in the slides. So that is 1 times 2z minus 0 times minus 1. Sorry. That is 1 times 2z minus 0 times minus 1, which gives you 2z. Finally, your joint distribution of y and z at the small point y and small z is the Jacobian determinant multiplied by the joint distribution of x1 and x2 evaluated at the solution values of x1 and x2, which was y minus z and z squared. Okay, yes?
When computing Jacobian, how do we determine the order of derivatives?
It doesn't matter. You can, if you change the order of x1 and x2 and do the same thing, it will give you the same answer. Okay, it doesn't matter which order you do it in. It would be very strange if it did. Yeah, it doesn't matter. Okay. Okay. All right. Let us continue. So that's a small example of showing you how to do that in the general case. So now, what we're going to do for the rest of today are something called moment generating functions, which is the next lecture. So moment generating functions, they're very useful in order to express moments of a distribution. What I'm going to do first is define what is a moment, because that might be quite important. So we've talked so far on this course about means and variances. Now, the mean and variance, you may or may not have heard them referred to as the first and second moments of a distribution. The mean would be the first moment. The variance would be the second moment. So for many random variables, the first 2 moments, that's all you need to know. For example, for a normal distribution, if I know the mean and variance, I know the entire distribution. I'm going to introduce the normal distribution later, but bear with me for now when I say that if I know the mean and variance of a normal distribution, I know the entire distribution. However, for lots of other distributions, the first 2 moments are not enough. So, for example, you might be interested in the third moment, which I'm going to talk about in just a moment. Many of you might already know that the third moment is something called skewness. It measures vaguely how lopsided the distribution is. So we're going to talk about 2 types of moments. Moments around the origin and moments around the mean. So a moment around the origin would just be the expectation of a random variable to a power. So we call that, I've used the notation mu r prime to refer to a moment around the origin. So that is the expectation, if our random variable is y, it's the expectation of y to the power of r. So the first moment is the expectation of y. The second moment is the expectation of y squared. Third moment, expectation of y cubed, so on and so forth. We would call those moments around the origin. Okay. Now, it's actually rather unusual to use moments around the origin. More frequently, we talk about moments around the mean. So that would be, instead of taking the expectation of y to the power of r, we take the expectation of the deviation of y from its mean to the power of r. Okay. So clearly, the first moment around the mean is 0, always. The second moment around the mean is the variance, and so on and so forth. Okay? So that's moments around the mean, moments around the origin. So now onto something, now that we know what a moment is, now onto something called a moment generating function. So moment generating functions are very useful things. They do exactly what it says on the tin. They allow us to generate moments. That is, if I want to know the rth moment of a particular random variable, I would do that using its moment generating function. Now you could also do it by integration, by computing all of these expectations, but it's usually much faster and much more convenient to work with something called a moment generating function. Okay, so you can always compute these expectations in the normal way by integrating for a continuous random variable or summing for a discrete random variable, but it is much faster and much easier in general to work with something called a moment generating function. Moment generating functions are crucial to prove things like central limit theorem, which we're going to prove later in this course. Central limit theorem, as many of you probably know, is fundamental for regression analysis, actually for basically all of econometrics. Okay. If you don't know what the central limit theorem is or why it's useful, don't worry, we'll get there. So we use moment generating functions to generate moments around zero, and we use a moment generating function because it's usually faster and more convenient than computing integrals. So what is a moment generating function? Suppose that y is a random variable which has a distribution function, fy of y. Then the moment generating function, so it's a function of t. I'll talk about what t is later, but for now just bear with me that it's my of t, is the expectation of the exponential of t times y. That is what a moment generating function is. Now, clearly, depending on whether y is discrete or continuous, you need to use the appropriate formula. If it is continuous, you need to integrate over the marginal distribution of y. You need to integrate e of ty. Okay, in the continuous case. In the discrete case, you would replace the integral with a sum to compute the moment generating function. And we're going to use a trick based on Taylor expansion of exponentials quite a lot, which I'll talk about in just a moment. Okay. So here is the main important thing you need to know about moment generating functions. This is from page 105 of the book. So if my of t is a moment generating function of a random variable, then we have the following: that the rth partial derivative of the moment generating function with respect to t evaluated at t is equal to 0 gives us the rth moment around the origin. Okay, so I differentiate my moment generating function r times with respect to t, then I evaluate that at t is 0, I get the rth moment around 0. Did I want to prove that? Yes, I did. Okay, so that is a very important theorem. I'm going to show you a proof, and then afterwards we'll apply it to some distributions. Okay, so this proof is going to make use of something called a Taylor expansion, which I'm going to begin by showing you what that is. It's going to be a Taylor expansion of the exponential function. So, let's prove that, well, I'm just going to write MGF, because it's the main theorem that's useful with respect to moment generating functions. So firstly, what is something called a Taylor expansion? For those of you who have not seen it before, a Taylor expansion of some function f of y at a point A is as follows. It is, so we can write that fy is equal to f of A plus f prime, so f prime meaning first derivative of f, times y minus a divided by 1 factorial plus f double prime of a times y minus a squared over 2 factorial plus, so double prime meaning second differentiate twice, plus f triple prime of a y minus a cubed over 3 factorial plus, and so on and so forth to infinity. So every time you increase what you differentiate by, so here we differentiate 3 times, you add a power, and you add you keep increasing in the denominator what's the factorial. So we're going to do a Taylor expansion.
Sorry, I'm just doing space.
Okay, no worries. We're going to do a Taylor expansion of the exponential function. So for us, we're going to use f of y. We're going to take it equal to the exponential of ty. Okay, that's what we're going to be interested in doing. And we're going to take a equals 0. So that's what we're going to do. Okay. Well, if we do a Taylor expansion, then we have the following. We have that e of ty is equal to e of 0 plus t e of t times 0 y minus 0 plus half t squared e of t 0 y minus 0 squared, and so on. I'll do one more term because I think we might need it later. Plus, so one more term, 1/6 t cubed e to the t times 0 y minus 0 cubed, and so on. Okay, so that's a Taylor expansion. It's a Taylor expansion for the exponential. You can plug in what that is. Obviously, everything to the power of 0 is just 1. So we're going to end up with 1 plus t y plus half t squared y squared plus 6 t cubed y cubed, so on. Okay, so the t's are going starting at power 0, and they're going up a power every time. And the y's are they're starting at y to the 0, they're also going up a power every time. And then here we have we divide by 1 factorial, here we divide by 2 factorial, here we divide by 3 factorial, so on and so forth. Okay, so let us now, so clearly we've done a Taylor expansion of this guy, because what we're going to be interested in is the expectation of this guy, which is our moment generating function. So let's take the expectation of this guy. So our my of t is the expectation of e to the ty. And now I'm going to plug in this guy, which is the expectation of 1. Clearly that's going to be a 1 plus t. Remember, t is not a random variable, t is just a constant. So if you take it out of this expectation, plus a half t squared e of y squared plus 1/6 t cubed e of y cubed, and so on to infinity. Okay, so that's my moment generating function. Now what I want to do, I want to show that if I differentiate this with respect to t, and then I evaluate that at t is equal to 0, I'm going to get a moment. And the moment I'm going to get is going to depend on how many times I differentiate. Okay, so let's look at the rth moment. So, for moment r, I'm going to differentiate with respect to t, r times. So that's dr my of t by dtr. So if it was r was 1, I'd differentiate once. Right, so what is that? Well, it's relatively straightforward to do because here we've just got a polynomial in t. Okay, it's easy to differentiate a polynomial. It's very straightforward. What we're going to get is the following. You can try this. You're going to have e of y to the power r plus e of y, what was it? Oh, sorry, r plus 1. E of y to the power r plus 1 times t plus e of y to the r plus 2 times t squared plus, well, that's all we're going to need, plus and so on and so forth to infinity. Okay, so everything which is of a power smaller than r is going to drop out when we differentiate r times. We're going to be left with this infinite sum here. Now what remains is to set t equal to 0. Okay, what I'm going to do now is I'm going to set t equal to 0 because that's what we're trying to prove. So now I'm going to evaluate this guy, dr my of t by dtr, and I'm going to evaluate that at t equals 0. That's what this line means here next to a derivative. If I write a line and then I put something equals 0, for example, that means evaluate this term at that point. Okay. So what is that? Well, here we've got a t. We've got to set that equal to 0. Here we've got a t squared. That's also going to be 0. Next we're going to have t to the 3, so on and so forth. Above here, we're always going to have t to the power of something. The only thing without a t in it is this first term here. So when I set t equal to 0, I get left with this term there. Okay, and that's it. So I differentiate r times. Sorry, this should be an r here, my mistake. Differentiate r times, evaluate at t equals 0, I get the rth moment around 0. We can draw the box. So, what did we do? We began by using a Taylor expansion for the exponential. The Taylor expansion is useful because it allows me to write an exponential as an infinite sum. And when I take the expectation of an infinite sum, because of the linearity of expectations, I can just write that as an infinite sum of expectations. Okay, so just go back. We start out with a Taylor approximation. Now I need to take the expectation of a Taylor approximation, so it's the expectation of an infinite sum. Because the expectation of a sum is the sum of the expectations, I can write it like this, which is very handy. Now I need to differentiate. If I differentiate r times, I skip that part, but you can try it. You're going to end up with something like this, or you're going to, not something like this, you're going to end up with exactly this. The first term you're going to get is the expectation of y to the power of r. Everything else is going to have t at least to the power of 1 multiplied by it. So when I set t equal to 0, those all go, and I end up with just the expectation of y to the power of r, which is the rth central moment. So why is this useful? I can get any moment now by differentiating something and setting and evaluating it at a point. Okay, it's much easier for almost all distributions, and I'm going to show some examples now, to do this than it is to evaluate moments using integrals. Usually much easier. Okay. And also moment generating functions are very useful for proving important things like central limit theorem. So, back to my desktop. So we can get the moment generating function like that. Some properties of moment generating functions. So suppose that g is a continuous single-valued function and y be a random variable. That means that for each y, g gives me one value. Y is a random variable with distribution function fy of y. Then, unsurprisingly, I can compute the moment generating function of g of y by taking the expectation of the exponential of t times g of y. So clearly when g is the identity, we get the moment generating function of y. When g is some other single valued function, we need to take the expectation of the exponential of t times g of y. And this, it follows directly from the definition of moment generating function. There's nothing to prove there. Okay, so if I have some other random variable, g of y, which is a function of y, I can compute its moment generating function like that. Now, a very useful property of moment generating functions is also that if I have one random variable, which is a sum of independent random variables, then the moment generating function of that random variable, which I call u here, is the product of the moment generating functions of all of the random variables. So if u is the sum of y1 up to yn, the y's are all independent, and they have their own moment generating functions, then the moment generating function of u is the product of the moment generating functions of the y's. Now, that sounds more complicated to prove than it is. It's actually very easy to prove, so I'll just do it very quickly. So I'm going to show that the moment generating function of a sum is the product of the moment generating functions when the random variables concerned are independent. Okay. So, this is quite easy. I'm going to write moment generating function of sum of independent random variables. So, u was y1 plus y2 plus y3 all the way up to yn, and the y's are independent. So now we want to derive the moment generating function of u. Okay, well, the moment generating function of u, so you write that mu of t. By definition of the moment generating function, that is the expectation of the exponential of u times t. Okay, let's plug in what u is. So that is the expectation of the exponential of y1 plus y2 plus so on to yn times t. Okay. Now, I'm going to rewrite this exponential here as the product of many exponentials. Okay. So it is the expectation of the exponential of y1t times exponential of y2t times exponential of y3t all the way up to the exponential of ynt. Yep, I have a sum in the exponent, that's the same as the product. Okay, now these y's They are all independent. So, therefore, the exponential to the power of t times y, they're all independent as well, for each y. So, what does that mean? It means that the expectation of this product here is the product of the expectations, because they're independent. So we have the following. And so on. Why? Because they are all independent. If y1 through yn are independent, then any function, like the one here, for example, they're all independent as well. And so the expectation of the product under independence is the product of the expectations. Okay. Well, that is just the product of the moment generating functions, by definition. By the definition of the moment generating functions. So here we needed independence. Without independence, this doesn't work. Okay? Say that one more time. If they are not independent, you cannot do this. Independence only. All right. So that's the results. Do I write a square? It was quite easy. Why not? Let's have a square. All right. Back to the desktop. So that's that result, which is important. Now, something which is very, very important indeed is equivalence of moment-generating functions and distributions. So, suppose that x and y are two random variables with moment-generating functions mx of t and my of t, respectively. Then x and y have the same probability distribution if their moment-generating functions are equal over all values of t. That is, if x and y have the same moment-generating function, they have the same distribution. Okay, that is, if I know the moment-generating function of x and y is the same, I know that they have the same distribution. Now, I'm not going to prove this for the general case, because it's quite complicated, certainly too complicated for this course. What I will do is prove this for a particular case when we have a discrete random variable with a range of values from 0 up to some value n. Okay. So it's true in all cases. I'm not going to prove it in all cases. I'm going to prove it in a particular case, which is what I've just written there, for a particular discrete random variable with range 0 up to n. Okay. So let's do that proof. This is a little bit involved, but I think it's important to show you, because this result is very, very powerful. And it's good that you have an idea of where it comes from. So, let's go to the .chem again. Okay. So as I said, I'm going to write MGF distribution. So that's what I'm trying to show equivalence of. So, we're going to consider a particular case where x is going to be discrete with range (0, 1, 2) up to n. So you could think of x as being like a count distribution if you want. Poisson would be an example of an x which takes that form. Okay, so we're going to do this particular case. So then, what is the moment generating function of x in this case? Well, mx of t, it is the expectation of e to the power of t times x. Now, because we're in a discrete world, we just need to sum over all the possible values and weight them by the probabilities. So we're going to sum. X is going to go from 0 to n, we're going to have exponential t times x, and we need to weight with the appropriate probability, which is the probability that our random variable is equal to small x. So that's our moment generating function. Now what we're going to do is we're going to take another random variable y, and that random variable y is going to have the same moment generating function as x, and then we're going to show that in that case then y must have the same distribution as x. Okay, so I'm going to start. Let there exist y such that mx of t equals my of t. So I'm going to take another random variable y with the same moment generating function. Okay, so let's do that. And then the aim will be to show that y must have the same probability distribution. So, well, we just wrote down what the moment generating function of x was. It's the sum x equals 0 to n e tx prob x equals x, and I'm going to do the same thing for y. So I'm working in a world of discrete random variables that can take values 1 to n. Okay. So y is going to also live in that world, and it's going to have the same moment generating function as x, which is going to be the sum. Y is going to go from 0 to n e of ty prob y equals small y. And that is going to be equal to 0. Because we're supposing that the moment generating functions of x and y are equal. Okay. So now, here I used a small y to index the sum. Right? I can use anything I want here. I used a small y because I was considering a random variable large y. I can actually use anything I want. I can use a, I can use b. What I am going to use is x. So, the first term stays the same. The second term, I'm just going to replace the index of my sum. Instead of using y, I'm going to use x. Nothing changes. It's exactly the same. It's just a labeling. All I've done is change labels. Okay. Instead of taking y from 0 through n, I'm taking x 0 through n. Why do I do that? Well, because then it becomes very obvious that I can combine these two sums, the first term and the second term. So I can combine these two sums. What I have is that the sum from x going from 0 to n of e to the t x times the probability that big X equals little x minus the probability big Y equals little x is 0. So that's just combining this and that into one sum. If I have two sums over the same indices, I can always combine them. Okay, so now let's just make our life a little bit simpler with some notations. So let S, I'm just going to call S be exponential of t. And something which is important is that S is strictly positive for any value of t. If I raise the exponential to a power, I get something positive. Right? That's important. So then, what I'm going to do also is let C of x be the difference in probabilities. So C of x I'm going to call prob x equals little x minus prob big Y equals little x. That's what I'm going to call C of x. So then, what do we have? If I plug those two definitions into my equation, I have that the sum of x going from 0 to n of s to the power of x times C of x is 0. Okay. So that is, well, it's a polynomial in S. Okay. It's a polynomial of degree n in S. Clear? S is strictly positive. Okay. So this is a polynomial of degree n in S. And S is strictly positive. Now, it's well known that if you have a polynomial of degree n, n being some positive number, in a positive variable, which is our S, that polynomial can only be 0 when all of the polynomial coefficients are 0. The polynomial coefficients are the C of x's. Okay. So, setting this, the solution to this polynomial equation can only be 0 if all of the C of x's are 0. That's a property of polynomials. Okay, I'm not going to get into why. Take my word for it, it's true. So if we have this solution, if we have this equation with that equal to 0, that must be, it must be the case that all of the C of x's are 0. Okay, can't happen any other way. It's impossible. So, what does that mean? Well, C of x equals 0 for x equals 0, 1, 2, all the way up to n. Our polynomial coefficients must be 0. So, what is C of x? It was the probability that big X equals little x minus the probability that big Y equals little x equals 0 for all x is 1, 2, n. Alright? And if that's the case, then clearly y and x have the same distribution, because the probability that they are equal to any point, to any value, is the same for all of those values. Therefore, if they have the same probability function, they have the same, well, that's the same as saying they have the same distribution. Okay, so what did we do? We did the following. So we're living, for the purposes of this proof anyway, in a world of discrete random variables with range 0 to n. So we wrote down what the moment generating function is. It's just a sum weighted by the appropriate probabilities. Then we supposed that there existed some other random variable, y, with the same moment generating function. We worked a little bit with the fact that they had the same moment generating function. Eventually, what we managed to show was that this, the fact that they had the same moment generating function, gave us an equation of a polynomial in a positive number of degree n equal to 0 with polynomial coefficients c of x. Now, because it's a polynomial of degree n in something positive, the only way that it can be equal to 0 is if all of the coefficients are equal to 0. Okay? Why? If I take a polynomial of a positive number, well, no, I'm not going to get into why. Sorry, I said I wasn't going to get into why. But that's the case. So then, if all of the coefficients are equal to 0 at every point, we have that the probabilities are equal, so they must have the same distribution. Okay. Now, as I said, let me go back to emphasize that the theorem is more general than the proof I just gave. The theorem doesn't require us to live in a world of discrete random variables with finite range. But the proof is complicated, so we're going to suffice with a simpler proof for today. Okay, so this is very powerful. It means that if I can show that two random variables have the same moment-generating function, I can show that they have the same distribution, which is very useful indeed. What does it mean? It means that the moment-generating function, provided that it exists, it contains all the information about the moments of the associated distribution. Let me say that again. The moment-generating function, if it exists, it does contain, obviously, we can get from it every moment of the distribution. If I can get every moment of the distribution, any moment you want, it's not particularly surprising that I can completely characterize the distribution. Okay, if I have a function which gives me every single moment to infinity of a distribution, it's not particularly surprising that that characterizes the distribution. I'm not going to get into why, but it does. So this and the two previous results, they are very useful in deriving the distributions of functions of random variables or showing equivalence of distributions. So what we're going to do, not now, because we're going to run out of time, we're going to derive some moment-generating functions for known distributions, and then we're going to get on to show you how functions of some known distributions give you other distributions. But I'm going to stop there for today. So next time, some examples. I'm going to start with Bernoulli, binomial, Poisson, so on and so forth. But we'll leave that for next week.